Right, in this slope deflection example, we've got this asymmetric frame. Columns are the same flexural rigidity, but they have different heights. And we have an asymmetrically placed vertical or gravity load, both of which are going to potentially cause sway one way or the other. Now, what's drawn on the page is a potential sway to the right. In a different video, we talked about how that actually may not make a lot of sense, that we're going to guess that it actually goes back to the left, but we're showing it to the right because that will give us a positive chord rotation for the two columns, along with them being tied to a positive delta. And so we anticipate that we're going to get negative values at the end of this numerical problem for delta, as well as for the chord rotations for both of those columns. Right, so remember slope deflection, we can identify the kinematic degrees of freedom. That's the known or unknown member end displacements. We know that with the fixed ended A, fixed ended D, that both of those rotations are zero. We know if we assume that there's no shortening or elongation of the columns, that means that there will be no chord rotation for the beam. All of those are going to be zero. We don't know what the rotation of B will be. We don't know what the rotation at C is. And we don't know the chord rotation values, although they can both be tied to this specific lateral translation at point C or point B. I've got it drawn there at point B. So the chord rotation for the left column will be delta over 6. That for the right will be delta over 3. Right? So we'll come along and we will establish that our symbolic value of K is I over 30. That comes from looking at the I over the L's of each of the members, finding a common denominator that goes along with everything. And I choose this only because I like to have integer values when I'm writing all this up by hand. It really makes no difference what you choose to use. It's just whatever is easiest as you go along. Right? For the fixed end moments, we only have one member that has a member load, and that's the beam. So of course you would come into whatever is your favorite table of fixed end moments. Here's one with an offset concentrated force. And so the thing I remember about this particular scenario is that it involves both the terms that are the short and the long distance. Really, it's not the short and the long distance. It's the distance from the left edge over to the load and from the right edge over to the load. The sum of those two has to, of course, be equal to L. And I just remember that, of course, it's going to be directly associated with the total axial, or not axial, but the total concentrated force. And then I'm going to have some sort of A times B times another thing over L squared. And I remember that it's going to be either B squared times A or A squared times B. And the way I figure that out is that if the load is closest to the support, then I'm going to emphasize the distance that's the bigger one, that the effect will get bigger the closer this load gets over to. I don't know if that's really the right way to think about it. It's just it's just a rule of thumb that I use if I don't have this table available to me and if I don't want to have to derive it along the way. Right? So PB squared A over L squared on one side, and of course then vice versa for the other. There's a plus and minus to take account of, and you'll note that when I substituted this in, that I've got the left one being a negative value. We're far away from B, right? So we're going to emphasize the short distance on that one, and so that's why that one's absolute value is smaller than the other one. And then note on the original work that, of course, on the right-hand side should be a plus, not a minus. So there's a typographical mistake, not the only one that's on this page. Right. So then you write out the slope deflection equation for each and every member and moment, that is. And I've crossed out already the values that are going to be zero, just to begin to make this a little bit easier. And then you substitute in then for the appropriate values of the K's. And this gets a little tricky to work through. Let's do one of these. Right, 2e KAB, so that's 2e times KAB, which is a 5k times theta b. Right, so that's where the 10k theta EK theta b came from. and then minus 6ek. KAB is again 5k times psi AB. Well, psi AB is equal to delta over 6. So the 6 will cancel out, and we're left with a minus 5ek delta term. Now, one more thing for shorthand reasons, just to make the equations of equilibrium a little bit easier to work with, I've got redefined B just equal to ek times theta b, and that's why you see a 10b and then minus a 5d. And so on and so forth for each and every one of these membrane moments. Now there's another typographical mistake here, that for MBC we've got 4ek BC. Well, KBC is 9k, so that's 4 times 9. That should have been 36 there, 18, 18, and 36 in those two equations, and so on and so forth, as you get ready to, or you're doing the setup to get ready for writing the equilibrium equations and substituting these equations in.